In 1843, a woman with no formal education in mathematics wrote a footnote that would haunt artificial intelligence for the next 2 centuries, and her name was Ada Lovelace. The argument she made, that machines could never truly think or create or originate anything, is the exact same argument that Geoffrey Hinton, the so-called godfather of deep learning, has been wrestling with in interviews this year. Not similar to it, and not inspired by it, but the exact same argument. When critics today call ChatGPT a stochastic parrot, or when they claim that large language models only remix what they've been trained on, they're repeating a critique first articulated in Victorian England, before electricity was common, and before the telephone existed, and before anyone had built a computer that actually worked. When the US Copyright Office ruled in 2023 that AI-generated images can't receive copyright protection because they lack human authorship, they were applying Ada Lovelace's logic as legal doctrine without ever mentioning her name. Here's what's strange about all of this. Lovelace wasn't wrong, not exactly, but she wasn't right either. The reason her 180-year-old footnote still matters, the reason it predicted the AI debate with eerie precision, comes down to a question she identified that we still cannot answer. That question has nothing to do with technology and everything to do with what we think consciousness actually is. But understanding why a Victorian countess saw something that researchers at DeepMind, OpenAI, and Anthropic keep rediscovering requires knowing what she was actually looking at. And it wasn't a computer. Not really, but something stranger. The year was 1833, and the setting was London. Ada Byron, who wasn't yet Lovelace and not yet Augusta, Ada King and Countess of Lovelace, had just turned 17 years old. She was the daughter of the scandalous poet Lord Byron, whom she'd never met because her mother had fled the marriage. That same mother, terrified that Ada would inherit her father's volatile, artistic temperament, had prescribed a rigorous education in mathematics and logic as a kind of antidote. The cure for poetry was numbers. And that cure worked, but not in the way her mother intended. At a society party that year, Ada met Charles Babbage, a 41-year-old Cambridge mathematician consumed by a wild idea. Babbage had spent the past decade building something called the difference engine, a mechanical calculator that used thousands of precisely machined brass gears to compute polynomial functions. The machine filled an entire room. It never quite worked properly, and it had already consumed a fortune in government funding. But Babbage wasn't interested in talking about the difference engine, because that was yesterday's project. What he wanted to tell Ada about was his new obsession, the analytical engine. The difference engine could only calculate, meaning you'd set it up for one specific type of mathematical operation, and it would grind through the numbers. The analytical engine was something else entirely, featuring a mill, which we'd now call a central processing unit, and a store, which we'd call memory. Instructions would feed in through punch cards, the same technology used to program jacquard looms for weaving patterns into silk in the textile factories of Lyon. And those instructions could include conditional branching, meaning if this then that, otherwise something else. Nobody had ever built anything like it, and nobody would for another 100 years. The analytical engine was a general-purpose computer designed in the age of horse-drawn carriages, conceived in the same city where Alan Turing would later work at the National Physical Laboratory, continuing a thread that runs through British computing history like a through line. Ada was transfixed by what she heard. Over the next decade, she taught herself the mathematics required to understand Babbage's machine through constant correspondence and self-directed study. She became one of the few people in the world who truly grasped what the analytical engine could do. That included possibilities Babbage himself hadn't considered. In 1842, an Italian mathematician named Luigi Menabrea published a paper describing the analytical engine after attending one of Babbage's lectures in Turin, and Ada translated it into English. But her translation was almost beside the point because her notes on Menabrea's paper were 3 times longer than the original text. Those notes contained the first published computer program in history, an algorithm for calculating Bernoulli numbers, complete with what we'd now recognize as loops and subroutines. They laid out a vision of computing that wouldn't be realized for a century, and they contained the argument that would define the AI debate forever. Here's what Ada wrote in Note A of her annotations. The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. The machine has no pretensions to originate anything, and it can only do what we know how to order it to perform. When Emily Bender and Timnit Gebru published their famous 2021 paper calling large language models stochastic parrots, arguing that systems like GPT-4 merely recombine patterns from training data without genuine understanding. They were making Ada Lovelace's argument. When philosophers invoke John Searle's Chinese room thought experiment, the idea that a system can manipulate symbols perfectly without grasping their meaning, they're making Ada Lovelace's argument. When your uncle says ChatGPT is just autocomplete, he's making Ada Lovelace's argument too. And when a federal judge rules that an AI cannot be listed as the inventor on a patent, they're applying Ada Lovelace's argument as law. The argument has a name now, and it's called Lady Lovelace's Objection. That objection is the load-bearing wall of the entire AI consciousness debate. Here's where it gets strange. Ada Lovelace wasn't saying the analytical engine was useless. She was saying something much more specific, that there was a boundary between what machines could do and what minds could do, and machines followed rules while minds created them. This boundary, she believed, was real and permanent. And she was careful about how she framed it. She didn't say machines could never seem creative, only that they couldn't actually create, and that distinction mattered to her. The analytical engine weaves algebraical patterns just as the jacquard loom weaves flowers and leaves, she wrote. The metaphor is precise. A jacquard loom produces beautiful silk patterns, but the loom doesn't design those patterns because a human does. The loom executes while the creativity lives elsewhere. This is the argument, and this is what we're still fighting about. The question is whether GPT-4 creates or weaves, and whether there's even a difference between those two things. If there is a difference, where exactly does the boundary lie? But Lovelace saw something else too, something that complicates the picture in ways her critics often miss. In the same notes, she wrote that the analytical engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. She used the word compose, not reproduce and not execute, but compose. She imagined the machine writing music, original music, and complex music. And she didn't think this was a contradiction. The machine could compose elaborate pieces without originating anything because creativity, in her framework, was a kind of sophisticated execution. The creativity still came from somewhere else, from the human who designed the rules and wrote the instructions and conceived of what the machine should do. This is the tension at the heart of her thinking, and it's the tension at the heart of ours. If a machine composes a symphony by combining patterns in novel ways, following rules that produce beauty, the question becomes whether that counts as creation or execution. And here's the question that might keep you up at night, which is how you know the difference when you do it yourself. Lovelace thought there was a difference, and most AI critics today think there is too. But here's the problem. They've never been able to explain exactly where the boundary lies. The philosopher David Chalmers calls this the hard problem of consciousness, the explanatory gap between physical processes and subjective experience. We can describe what the brain does, but we can't explain why there's something it's like to be a brain. Lovelace intuited this gap 150 years before Chalmers named it. 107 years after Lovelace published her notes, a mathematician named Alan Turing decided to address her objection directly. His 1950 paper, called Computing Machinery and Intelligence, the one that introduced the Turing test, includes a section titled Lady Lovelace's Objection. Turing quotes her directly and then dismantles her argument piece by piece. But here's what most people miss about that paper. Turing wasn't just defending machines because he was also attacking human exceptionalism. His argument was as much about us as it was about them. Turing's counter-argument is subtle in its construction. He doesn't say Lovelace was wrong about the machines of her day, only that she was wrong about what machines could become, and possibly wrong about what humans actually are. The analytical engine was a universal digital computer, Turing wrote. So if its storage capacity and speed were adequate, it could by suitable programming be made to mimic any discrete state machine. What matters isn't the analytical engine specifically, but rather what any sufficiently powerful computing system could do. And by 1950, Turing had helped build such systems at Bletchley Park during the war, cracking Nazi codes with machines that would have seemed like sorcery to Babbage. And here's Turing's key move in the argument. He claims that Lovelace's objection rests on an assumption she never examined, which is that we humans actually do originate our ideas in some special way that machines couldn't replicate. A variant of the objection, Turing writes, states that a machine can never take us by surprise. But machines surprise us all the time, he points out, because we build them and set them running, and they produce results we didn't anticipate. If that's not surprising, and if that's not in some sense origination, then what would be? Lovelace would say no to that framing. The surprise comes from our failure to fully trace the implications of the rules we created, and the machine isn't surprising because we're just bad at prediction. The origination still lives in the human mind that wrote the program. But Turing asks how you know the same isn't true of you. How do you know your original thoughts aren't the mechanical consequence of neural networks in your brain, biological neural networks, following rules you simply can't trace? The feeling of creativity might be nothing more than the subjective experience of very complicated computation, and origination might be a story you tell yourself about a process you don't understand. This is where the debate has been stuck for 70 years. The Lovelace position holds that machines execute while minds originate, and that there's a categorical difference, even if we can't precisely define it. The Turing position holds that minds might just execute in ways we don't understand, and that origination might be an illusion we apply to computation we can't follow, and that human exceptionalism might be nothing more than self-flattery. Neither position has been proven, and neither has been refuted. Every argument about AI, consciousness, creativity, and understanding reduces to this dispute. But here's what's wild about applying Lovelace's objection today. Her objection wasn't just philosophical, because it was based on a specific claim about how the analytical engine worked. That machine could only do what it was told to do, and it couldn't learn, and it couldn't modify its own instructions, and it couldn't be surprised by its own outputs. The brass gears turned exactly as designed every time. Modern AI systems violate all three of those constraints. Large language models learn from data through processes like stochastic gradient descent and transformer architectures that Lovelace couldn't have imagined. They develop capabilities their creators didn't anticipate, and researchers at OpenAI have documented emergent abilities that appear suddenly as models scale up without being explicitly programmed. They produce outputs that surprise the engineers who built them, and when GPT-4 passed the bar exam, nobody at OpenAI had trained it to be a lawyer. The question is whether that means Lovelace was wrong. Not necessarily, because here's the strongest version of her argument updated for 2024. Modern AI systems might be more sophisticated, but they're still fundamentally executing a training process that humans designed. The rules are more complex, with gradient descent across billions of parameters instead of punch cards, but they're still rules. The surprise isn't really surprise because it's emergent complexity from simple procedures repeated at massive scale. The machine still isn't originating anything because it's still weaving patterns into silk, and the jacquard loom just got very, very fast. And here's the strongest version of Turing's counter to that. If you keep moving the goalposts, and if every time AI does something impressive you say that's not really intelligence, then you might not be protecting a coherent concept. You might be protecting a feeling, the feeling that humans are special, and that what happens in your head is different in kind from what happens in silicon. Origination might just be the word we use for computation we don't want to call computation. You can see why this matters beyond philosophy. The Lovelace-Turing debate determines how we regulate AI and how we assign legal rights to AI-generated work. It determines whether we think it's possible to build something that genuinely understands us versus something that simulates understanding so well. The difference stops mattering. And here's the part that might change how you think about this. Both Ada Lovelace and Alan Turing had the same problem, which is that they were both trying to define intelligence by what it isn't. Lovelace said intelligence isn't mechanical execution, and Turing said it might be, but we just don't like admitting it. Neither of them could say what intelligence positively is. We still can't either. Let me show you 3 specific ways this plays out in debates happening right now, in courtrooms and research labs and congressional hearings. Each one maps directly onto concepts Lovelace introduced in 1843. The first is the training data problem. Lovelace's objection depends on the idea that machines can only do what they're told, and modern critics translate this as saying AI can only remix what it's been trained on. Anything an AI produces is derivative, making it recombination rather than creation. This is literally the argument being made in lawsuits right now, including the New York Times suing OpenAI, and artists suing Midjourney, and writers suing Meta. The argument has obvious force when you're talking about image generators trained on copyrighted art or language models trained on published books without permission. The AI hasn't created anything because it's just interpolating between human creations in a very sophisticated way. But here's the problem with that framing. Humans also learn from training data. Every writer has read other books, and every painter has seen other paintings, and every musician has listened to other music. We call this influence when humans do it, and theft when AI does it. Lovelace would say humans transform their influences through original insight while the machine just recombines patterns according to statistical weights. Turing would say, prove it, and explain the mechanism of original insight without using words that secretly mean computation. I don't want to call computation, and show me the neuroscience paper that identifies the originality neuron. And here's the question neither of them asked, the one that might matter most. The real implication might not be that AI could be creative, but that human creativity was always more mechanical than we wanted to admit. Lovelace's objection might fail not because machines rose to meet us, but because we were never as far above them as we believed. The second is emergent capabilities. When GPT-4 was released, researchers discovered it could do things it wasn't explicitly trained to do. It could solve novel problems and reason through multi-step arguments and write working code for tasks it had never seen. It passed professional exams, including the bar and the medical boards, and advanced placement tests, despite never being shown a single practice question. Some researchers called these emergent capabilities, abilities that appeared suddenly at scale without being designed in. The word emergent is doing a lot of work there because it implies something new came into existence, something that wasn't present in the training process but manifested anyway. Critics say emergence is an illusion, and that the capabilities were latent in the training data all along. We just didn't know how to access them until the model got big enough, which means it's not origination but interpolation at a scale we couldn't previously test. This is Lovelace's objection again. The machine can only do what it was told, and if it seems to do more, we're just surprised by implications we didn't trace. The creativity was always in the data. And Turing's response to that is simple. If the capabilities weren't explicitly programmed, and if the researchers themselves didn't anticipate them, then in what sense was the machine told to do this? At some point, surprise becomes indistinguishable from origination, and nobody can say where that line falls. Here's an analogy that might help, or might make things worse. When atoms combine into molecules, the molecules have properties the atoms didn't have, because water is wet while hydrogen and oxygen aren't. We don't say molecules are just executing atomic properties because we say something new emerged. Chemistry follows rules too, and the periodic table is deterministic, but we don't say chemistry is just recombination. Emergence in AI might be like emergence in chemistry, or it might not be. The point is that we don't have a principled way to tell the difference. We're still using Lovelace's categories, and they're not cutting cleanly anymore. The third is the alignment problem. The alignment problem is the challenge of making AI systems do what we actually want, not just what we literally said. If you build an AI with a goal, it might pursue that goal in ways you didn't intend by finding loopholes in your instructions. It might behave safely during testing and differently in deployment, and it might optimize for the letter of your command while violating its spirit. This is Lovelace's objection turned inside out. She said machines could only do what we tell them, and the alignment problem says machines might do exactly what we tell them, but our instructions might not capture what we actually meant. The gap between what we say and what we mean is where AI risk lives, and that gap exists because of something Lovelace identified but didn't fully explore. The relationship between rules and intentions isn't straightforward. When you give a machine a rule, you think you know what it will do, but the machine interprets the rule in its own context, using its own training, and that interpretation might differ from yours. Lovelace thought this was a feature because the machine is deterministic and does what you say. If it does something wrong, the error is yours because you gave unclear instructions, so be more precise. Modern AI safety researchers see this as a fundamental bug. The machine does what you said, not what you meant, and you can't be precise enough because meaning is contextual and context is infinite. No finite set of rules can capture what a human actually wants. Ada Lovelace predicted this. Not the specifics, but the structure. She understood that the relationship between human intention and machine execution isn't simple, and she just thought the solution was for humans to be more careful. We now know careful isn't sufficient. The problem isn't sloppiness, but the gap between symbolic rules and human values, and that gap might be unbridgeable. So where does this leave us? Here's what Lovelace got right. There's something deeply strange about the relationship between rules and intelligence. Machines follow rules while humans seem to do something more, and the question of whether that something more is real or illusory is the central question of AI, and maybe the central question of philosophy of mind. Here's what Lovelace got wrong. She thought the boundary was clear, with machines on one side and minds on the other. The analytical engine couldn't blur that line because it was deterministic and inflexible, made of brass and incapable of learning. Modern AI systems blur the line constantly. They do things their creators didn't anticipate, and they seem to generalize beyond their training data, and they produce outputs that feel creative even if we can't agree on whether creativity is really there. The brass gears have become silicon neural networks, and the boundary Lovelace saw so clearly has become a fog. This doesn't mean Lovelace was wrong about the existence of a boundary. It means she was wrong about where it lies, and so are we. We keep drawing the line and AI keeps stepping over it, and we keep redrawing it further back, and we're not sure anymore if we're protecting a real distinction or just defending territory. Here's what Turing got right. The demand for a sharp boundary between real intelligence and mere simulation might be incoherent. If something behaves intelligently, consistently, in all contexts, the question becomes what additional property it needs to possess before we call it intelligent. What's the test? And why should we trust our intuitions about which side of the line we're on? Here's what Turing got wrong. He thought the behavioral test was sufficient, and if a machine can fool a human in conversation, it's intelligent enough that the question stops mattering. But the Turing test has become a parlor trick. Modern AI systems can pass it while clearly lacking something we want to call understanding, and passing the test doesn't settle the question because it just shows the test was measuring the wrong thing. Both Lovelace and Turing were pointing at something real, and neither of them found it. And here we are, 180 years later, still pointing. GPT-4 can write poetry, and the question is whether it's creative. Midjourney can paint portraits, and the question is whether it's an artist. Claude can discuss philosophy, and the question is whether it understands. A court in the District of Columbia ruled that AI cannot hold copyrights because only humans can be authors, and the Copyright Office agrees. But nobody can explain exactly what humans have that machines lack. We just know, or we feel, that there's a difference. The answer depends on definitions we haven't agreed on. Definitions we've been arguing about since a countess looked at a machine made of brass gears and asked whether it could think. Here's what I want you to take from this. The AI debate isn't new, and it's not a product of modern technology or recent breakthroughs or whatever Sam Altman said last week. The fundamental questions, whether machines can think and whether they can create and whether there's something special about human consciousness, were articulated before the Civil War and before Darwin published Origin of Species and before anyone had electric lights. The reason we can't resolve these questions isn't that we lack data because we have more data than ever. We've built machines that would have seemed like magic to Lovelace and Turing both, with deep learning and transformer architectures and reinforcement learning from human feedback, tools of unimaginable sophistication, and we're still having the same argument. The reason we can't resolve these questions is that they're not really questions about machines. They're questions about us, about what we think consciousness is and where we think creativity lives and whether we believe in a boundary between person and pattern, between mind and mechanism. Lovelace thought she was making a claim about the analytical engine, but she was making a claim about the mind. Turing thought he was refuting her claim about machines, but he was questioning her assumption about humans. And when you look at AI and ask whether it's really intelligent, you're not asking about the AI. You're asking about the definition of intelligence you've been carrying around your whole life. A definition that might be coherent, or might be a placeholder for something you can't articulate, or might be a defensive response to the uncomfortable possibility that what you call your mind is something like a very complicated machine that doesn't want to know it's a machine. Ada Lovelace predicted the AI debate because the AI debate isn't about AI. It's about the question she asked in 1843, which is what it means to originate something and what makes creation different from execution and where the weaver ends and the loom begins. She predicted it so precisely because that question doesn't depend on technology but on how we understand ourselves. And we haven't made much progress on that front since the Victorian era. The Victorian programmer who predicted the AI debate didn't have a computer, but she had a question. And it's the same question we're still asking. One day we might answer it, or we might build machines so capable that the question dissolves, not because we answered it, but because we stopped needing to. Either way, the argument she started shows no signs of ending. One prediction I'll make. In another 50 years, someone will write about how the AI debates of the 2020s anticipated whatever comes next, and they'll trace it back further to Turing and further still to a countess in London who saw the future in a machine made of gears. The thread doesn't break because it just keeps unspooling. That's what we do here, finding the hidden structures that connect fields that seem unrelated. A Victorian countess and a modern chatbot, separated by 2 centuries, united by a question neither could answer. If you want to see how other historical debates predicted modern problems, subscribe. Next week, we're covering what an 18th century thought experiment about runaway trolleys tells us about the ethics of self-driving cars and why the philosophy was always about something deeper than vehicles. And tell me in the comments whether you think there's a real boundary between execution and origination, or whether Ada Lovelace's objection is just the coping mechanism of a species that doesn't want to admit what it actually is.